Hello and welcome back to enrichment simultaneous equations. Today we're trying to solve the system of equations x cubed plus y cubed is equal to 26 and x squared y plus xy squared is equal to minus 6. Now, where do we start with something that looks like that is the question. A few initial observations. First of all, there will be a symmetrical solution. What do I mean by that? If you look carefully on the left hand side of this, if you swapped x and y on the first equation or on the second equation, so the y goes there and the x comes there, and the same thing on the other term, the two equations are in fact unchanged. So what that means basically, if for example 1, 4, x1 and 4 is y works, then quite clearly it should work the other way around as well, 4, 1. So that is definitely something that should be happening with these two equations. Another thing that we should notice from this particular equation, okay, that possibly one of these numbers has to be negative, because of course we got square quantities in there, and therefore if we're ending up with a negative when we add them together, then the one of the x's or the y's is negative. So that is another little observation. It might be of no real use in all of this, but we just keep it in mind. Okay, so let's see where we're going to start with all of this. Where can you find questions like this? In my site, madasmaths.com. You can find on these booklets, standard, and the book is called Equations Advanced Skills. I think for this particular type of equations, they have a special name actually. I think I have probably about 6 or 7, maybe more. I can make another one just right now. This, of course, I didn't make it now. It's been sitting there for years. Okay, how do we approach it now? I'm going to show you two different ways for doing this particular equation. And the first one is the standard way. And the second one, it will work in this particular case because of a special structure that we have in there. So the standard way for something like this is to divide your equations side by side because they have a special feature. So let me just do that. And I will explain what the feature is and what I'm looking at. Oops. Let's write it dividing. I'm not going to put the extra line. I'm going to just write straight away. But when we do that, we should get 26 divided by minus 6. The special feature that appears in there is on the left hand side, this fraction has a homogeneous structure. What does that mean? Homogeneous, it also has the same meaning when you look at first order differential equations. If you look at one of my lectures, I'm not quite sure how to spell this, homogeneous, something like that. If I'm misspelling it, please forgive me. My spelling is not the best. Okay, it has a homogeneous structure, and the same term is used in differential equations in the same context. What this means, let's look at the fraction. I'm not going to give you the formal definition of that because it's actually easier to see it in a very simple, with a couple of simple examples. For example, if you have x, y, you had an x, you had a y, and then x, y. And let's say there you had x squared, y squared, x to the 4, y to the 4, and then you had x, y cubed. Pluses or minus, doesn't really matter, something like that. This is homogeneous. Each and every term within the fraction is of the power of 4. 2 plus 2, 4, 4, and that's a 1 times 3, which is a 4. Okay? If that was x to the 4y, this breaks. That is no longer of this particular type. Okay? What about if we had there something else such as, okay, that's what I have in there, I don't even remember what I had in there, something like this, or x to the 4. It was before. What if I have a number plus 7? Is that homogeneous? The answer is no, as it is. I can create homogeneous bit by splitting the fraction somehow and create a homogeneous fraction plus 7 over this, but this is no longer homogeneous. Okay, enough of this. I don't want to go away from what we're trying to do in here. This is homogeneous because each and every term on this particular fraction is cubic. Cubic, cubic. 2 plus 1 is 3, 1 plus 2 is 3. And when that happens, we can use a substitution. And the idea is exactly the same with the substitution we use in differential equations. We're going to use the substitution. We're going to call our y or our x, I prefer to do the y, is equal to some variable, some parameter. You can use any letter you want. I'm going to use lambda for this particular one. Y is lambda x. So I'm going to substitute this particular thing into my equation now that has reduced to a single equation in there, and see what happens. X cubed plus lambda cubed x cubed over, I'm going to get a lambda x in there, so it's going to be lambda x cubed. And here I'm going to get a lambda squared for squaring that. So plus lambda squared, x squared times the x cubed. And let's cancel this fraction down as well to 13 divided by minus 3. I'll put the minus at the front. It doesn't really matter. Let's put it at the top. 13 dividing, what did that do? Divide by 2. So over 3. And you can see why this substitution works. And the idea is exactly the same in differential equations. If you look at what happens in here, all the x's cancel all the way through. So we're going to get 1 plus lambda cubed over lambda plus lambda squared is equal to minus 13 over 3. So my equation rather lost its two variables, and now it's a single equation in one variable. It's going to create a cubic, which is a little bit of a pain to factorize or to deal with unless it has nice answers. And I can actually see that this particular one has a nice answer if you look a little bit ahead. I can see that lambda is equal to minus 1 is a solution in there. Let me explain to you how I see this. I'm going to do the other way as well afterwards. This is a difference. Let me write it. Let's write the lambda cubed plus 1. So I'm going to come out of this so you can see what I'm looking at. There's an identity, which is of course the sum of cubes, which says a cubed plus b cubed is identically equal to a plus b, a squared, and then we have a minus in the middle, ab plus b squared. You can verify that very easily by multiplication. So if I use this identity for this, that's 1 cubed basically, I'm going to get lambda plus 1, and then I'm going to get lambda squared minus lambda plus 1. So that's my numerator. And if you look at your denominator, which of course was lambda squared plus lambda, just wrote it backwards, of course you can factorize the lambda at the front and the lambda plus 1. Can I cancel that? You can, only if you take it into account that this is now the lambda is equal to minus 1 that disappeared, because of course if you look what's going to happen there, okay, so this is now, I can replace this with minus 13 over 3, and then I'm just going to just do it very quickly, times this across, lambda plus 1. You cannot just divide the bracket lambda plus 1 because of course you're going to lose one of the solutions. However, if you account for it, lambda is equal to minus 1, then of course you can cancel it and say, okay, I've taken care of that. I'm aware the solution lambda is equal to minus 1 is there, and then deal with the resulting quadratic. So this eventually will go to a quadratic. Let me just finish it off from here, and then I'll show you. Suppose you didn't see that and you didn't know the sum of cubes identity. So what's going to happen there? Times it across, so you're going to get 3 lambda squared minus 3 lambda plus 3. That's this 3 coming across, and then it's going to be equal to minus 13 lambda and 3 lambda squared minus plus 10 lambda, sorry, taking that to the left, plus 3 is equal to 0. And of course we can factorize that very, very easily. Hope we can see that is a 3 lambda, and we need the 3 there to make it all work And of course, the solution would have been lambda is equal to -1, lambda is equal to -3 from this bracket here, and lambda, of course, is equal to -1/3 from this bracket here. But let's, as I've said, we didn't know this, we didn't spot this. Okay, let's see, what can we do? We got a cubic. Can we sort out this cubic? Well, times it across. 3 lambda cubed plus 3 is equal to -13 lambda, -13 lambda squared. And then let's put it in its usual form. 3 lambda cubed plus 13 lambda squared plus 13 lambda plus 3 is equal to 0. So when we look at this now, of course, we should be looking for some factors, the factor theorem and so on. So if we look at this question carefully, because we got a 3 and we got a 3, we got a 13 and we got a 13, quite clearly maybe ones or -1s might work. Clearly 1 does not work because it's going to make everything positive. But if you check very quickly by inspection, if lambda is equal to -1, this is going to give you -3. If that's -1, it's going to give you +13. -1 is going to give you -13. And of course plus 3, and you found the factor. And if you found the factor, you can of course factorize it because you can reduce it to a quadratic. I'm going to do it here. So by inspection, lambda is equal to -1 is, I'm writing half uppercase, half lowercase. What's happened to my brain these days? I don't know. By inspection, lambda is equal to -1 is a sol. So we can proceed from there. I don't really want to do a long division here. It'll take too much space, too much rubbing off. So I'm going to do it like this. So have a look at that. 3 lambda squared, bracket, lambda, because lambda -1 is solution, so the bracket lambda plus 1 is in there. Okay, so this is my 3 lambda squared. By doing that, I created a 3 lambda squared, and I have 13 lambda squared, so I need to add to that 10 lambda. So I'll have the if you want, I'm looking at this term here. There's the 3 lambda squared, and I need another 10 lambda squared. I'm not writing 10 lambda squared though. I'm writing it like this. So 3 lambda cubed plus 3 lambda squared plus 10 lambda squared, 13 lambda squared. But now I created the plus 10 lambda. And I don't have that particular quantity, that I have 13 lambda, and now I created 10 lambda. So I need to add another 3 lambda. So in this particular case, I can write it like this. There's my 3 lambda that I need to add, and of course plus 3 there is equal to 0. And I'm expecting, of course, to happen. It's just long division, but run in a very bizarre way. So I can factorize now the lambda plus 1 on the other side from each of those terms. If you didn't follow that, or you say, oh my god, I don't really want to do something like this, just do a long division on your side or whatever method you're using, and you're done. And of course, we're going to have lambda plus 1. Oops, I'm writing it again like a pillock because my brain is stalling at the moment. I've just factorized that a few minutes ago. And that, of course, is all factorized. So I found 3 possible values of lambda. And that is -1, -3, and -1/3. That could possibly help me solve my original system of equations. Because remember, this is not, what am I trying to do? I'm trying to find an x and a y. I found lambdas. What's going on with all of this? Well, for each of them now, or each value, I have a relationship which says y is equal to -x, or y is equal to -3x. So I know this is now what I need to do next. So let's make some space. And let's see how we're going to deal now with the final solution. So I'm going to leave that because we need it. So we're going to look first of all at the lambda is equal to -1. So if lambda is equal to -1, that's the first case, this relationship, this substitution, becomes y is equal to -x. what I'm going to do with that next? Well, I can put it either here or here and find my x and my y. I'm going to put on the top equation. I think it's slightly easier. So if I put y is equal to minus x, this is my x cubed, and if I cube this, is going to give me now a minus x cubed is equal to 26, which of course is total rubbish. I have inconsistency. Inconsistency. What does that mean? Well, it means basically this is perhaps a solution that is, I don't know, it's not a proper solution of this particular system of equations. It does happen sometimes, and I'm glad it happened, particularly if you haven't seen something like that before. Okay, it could have done a mistake, of course, I'm not ruling that out, but for the time being, let's leave it at that and see if we see something sensible out of the other two possibilities for the lambda. So lambda is equal to -3, so that means your y is equal to minus 3x. Okay, so I put it again in the first equation, so it's going to give me x cubed. Oops, I'm writing stupid things here. Lambda is equal to -3, so my y is equal to minus 3x. So for this one was y is equal to minus x. For this one is just looking at this. So x cubed. I'm putting now this into my y equation, so that's going to cube into a negative. Minus 27x cubed is equal to 26. Minus 26x cubed is equal to 26. I feel much more comfortable seeing now decent numbers in all of this. I go x cubed is -1, which means of course my x is uniquely -1, and my y from this relationship is going to be equal to 3. Okay, so we can check this very quickly just to make sure it does balance the equations that we got up there. I can see obviously clearly that it balanced the first one, and this is going to be 1 times 3, so we got a 3, and then we got there a 9 with a -1 at the front, so it's -6, so it does work. So this, in fact, we haven't made any mistakes, so this is just clearly a problem. Okay, we're going to look at the third and final case. I'm going to wrap this off. So the final case is, of course, if lambda is equal to -1/3. Okay, so in this particular case, let me write things properly and organized, because as you can see, I make stupid errors. I'm getting too old, and I make omissions as well, all sorts of things. Okay, we're going to put that in our first equation again. It's the easiest. X cubed, and now I'm substituting -1/3 x to be cubed for my y, so it's going to go -1/27 x cubed is equal to 26. I'm expecting, I forgot to mention it, you remember now in the beginning I said this is a symmetrical situation. If we swap x and y's, we better get this the other way around. In other words, x is 3 and y is -1. I hope, anyway. Okay, so let's have a look at all of this. Times by 27. 27x cubed minus x cubed is equal to 26 times 27. What is that? I couldn't care less. It's 26 times 27. And then this will give me 26 x cubed is equal to 26 times 27. Divide both sides by 26. X cubed is equal to 27. And of course, x is in fact 3, as we expected. And if we look, putting now that x is equal to 3, into this relationship, if we put 3, we're going to get, of course, y is equal to -1. And these are the two solutions pairs are the only real solutions that balance this particular set of equations. Okay, this is the standard method when you spot something which on division produces a homogeneous fraction. I did say in the very beginning, this particular set of equations can be done in a very different way because it's special, it has a special structure, and is worth exploring this. This doesn't always happen, and it requires more identities that involve cubing and things like that. Let me write something down first of all, so you can actually see where I'm going with all of this. A plus B, not a cubed plus b cubed this time, but cubing it, your binomial. You should know that it's a cubed plus 3 a squared b plus 3 ab squared plus b cubed. And I'm looking at the left-hand side of this equation, and I cannot help seeing things from this particular identity. So what I can do there is I can write the first equation again, x cubed plus y cubed, as it is, and I'm going to triple the second equation underneath it. So I'm going to say 3x squared y plus 3 lots of xy squared, quite clearly is negative 18. So if I add these two equations now, the left hand side will produce x cubed plus 3x squared y plus 3x y squared plus a y cubed is equal to 26 take away 18. Is it 8? I hope it is. All right, let's look at this and let's look at the line above. This is the perfect expansion of x plus y cubed is equal to 8. So 8 is a good number because of course the cube root is unique. So x plus y is in fact equal to 2. So it's telling me that the two numbers that I'm looking for must have a sum of 2. I can at this stage solve for x or y because this is a much simpler equation, perhaps substitute into any of these, but I reckon I can do better than that in this particular case. Let's look at this particular equation and let's rewrite it, because of course on the left hand side there is a common factor of xy and xy. It will leave us inside there x from the first term and y from the second term is equal to minus 6. But of course my x plus y is equal to 2. So this can reduce to 2xy is equal to minus 6. And I have another equation here. And the other equation should say xy is equal to minus 3. I don't think I want to continue with this question. I'm sure this is now you can give it to a GCSE student to finish it off. It's just a standard kind of like simultaneous equations, which is about 3 lines to solve from this particular one. And of course it should give us the answer that we got before. In fact, just looking at it, I didn't expect to be as simple as that when I first looked at it. But the first method, please do not ignore it, because this is more general. This happened of course because the second approach, because this was perfect. Imagine there now we had something like a 2 here. The first method will still work because of course when you divide again you get a homogeneous fraction and you can do exactly the same things. However, now you cannot create this perfect cube that we did just now. Okay, I hope you enjoyed it. I hope you learned quite a lot from this particular lecture. I'll see you very soon. Who's laughing now?